I'm going to start this lesson looking at the scaling ratios for volume for different similar figures. So here we're going to fill out the table. We want to write the ratio of the side lengths A to B by comparing corresponding sides, and then we're going to compute the volume and see what the volume ratios are. So the first pair of objects, these are cones, and we haven't talked about the formula. We defined a cone, but we haven't talked about the formula for the volume of a cone yet, so I'm going to do this one for you. But the ratio of side lengths, we can choose any pair of corresponding side lengths, and since they're similar, the ratios are going to be the same. From A to B, we're going to say figure A is the bigger one and figure B is the smaller one. The ratio is going to be 5 to 4. Now, if you calculated the volume of the larger cone ends up being, in terms of pi, I'm going to leave everything exact, 250 pi over 3. And then the volume of the smaller cone, again in terms of pi, ends up being 128 pi over 3. So if I were to take the ratios, they both have pi in them, and they both are divided by 3. So when I take the ratios, the things in common are going to divide away. So in essence, the ratio from big to little is 250 to 128. If you were to reduce that down, that would reduce down, you could cut each of these in half, and it's going to reduce down to 125 to 64. So you might not realize the relationship between 5 and 125 and 4 and 64, but 5 cubed is 125 and 4 cubed is 64. So it looks like from this first example we can find the ratio of volumes by taking the scale factor and cubing it, which kind of makes sense because we did that with areas and we found out that the ratio of areas is the scale factor squared. So the ratio of volumes should be the scale factor cubed. But we'll do a couple more examples just to verify. So these two examples you should know the formulas for the volume, but the scale factor to begin with from A to B is going to be 1 to 5. So that's 1 to 5. The volume of A, which is the smaller one, is just what you get when you get the product of 2 times 3 times 1. So the volume of A is going to be 6. And the volume of B is going to be 10 times 15 times 5. That ends up being a whopping 750. So that's a big difference between those two. But if you look, just the linear scale factor is 1 to 5. So this guy should be, each linear length is 5 times as big as the original linear length. So the ratio of volumes is going to be even larger. So that ratio is 6 to 750. If you were to reduce that down, that ends up being 1 to 125. Again, 1 cubed is 1, and 5 cubed is 125, so this principle seems to hold. Let's do the next one. They have triangular bases, so the volume, or the ratio, again, if you choose corresponding sides, would be 4 to 12, which ends up being 1 to 3. Calculating the volume will say figure A is the smaller one. That's 1/2 the base times the triangle height, and then times 12. So that ends up being 144. And then the volume of the larger one, using the same formula, ends up being 3,888. So taking their ratio and reducing that down, it's 144 to 3,888, and that reduces down 1 to 27. Once again, we see the same property. 1 cubed is 1, 3 cubed is 27, so the property seems to hold. And we can solve it generically. We might do that in class to show you that it's going to be true regardless of what shape we use. So now we can write our scaling principle for volumes. So here it is. The ratio of volumes of similar objects is equal to the ratio of the corresponding sides cubed. So instead of squaring it, we're going to cube it. So whatever our scale factor or the ratio of corresponding sides is, we've got to cube it to get the corresponding ratio of volumes. And we'll work some more of those problems in class. But it's not always the case that we have similar figures. We can take some three-dimensional object and scale it by different values, just like we did for area. So we're going to show that in this next example. Here is a triangular prism, and we want to first calculate the volume of the triangular prism. So volume is always the base area times the height. In this case, the base area is going to be 1/2 the 3 times the 3, and then multiply it by the height here. So base area is 1/2 times 3 times 3. That ends up being 4.5. So my volume is going to be 4.5 times 5, and that gives me 22.5. So there's my original volume. Now, if one side of the triangular base is scaled by a factor of 2, and the other side is scaled by a factor of 4, and the height by a factor of 3, we're going to write down the new dimensions. So one side is 3, scaled by a factor of 2, that dimension is 6. The other side is 3, scaled by a factor of 4, the new dimension is going to be 12. And then the height is 5, and it's scaled by a factor of 3. That dimension is going to be 15. So we're going to calculate that volume, and that volume is going to be 1/2 the base times the height of the base times the height of the whole prism. So 1/2 times 6 times 12 times 15. That volume ends up being 540. So if you think of the new prism compared to the old one, they're not similar because not all the sides are in the same proportion. But if I multiply these scale factors together, 2 times 4 times 3, that's going to give me a ratio or a scale factor of 24. And if you take the original 22.5 and multiply it by 24, you're going to come up with 540. 24 times 22.5 is 540. So if you want to scale something with different dimensions, you have to multiply all the scale factors together. And that's going to get you your new volume. So the scaling principle with different scale factors is basically you're going to multiply the three factors together. So it's the product of the three factors. Instead of cubing a single factor, it's the scale factor with three different dimensions. You're going to multiply the three factors together. Okay, so we're going to do another example here. Use the rectangular prism shown to answer the questions. Calculate the volume of the rectangular prism. Again, that's pretty basic. It's the multiplying the three dimensions, 1 times 8 times 12, and that ends up being 96. So here we go again. If one side of the rectangular base is scaled by 1/2, the other side by 24, and the height by 1/3, we're going to first find the dimensions of the scaled prism. So I'm going to multiply 8 by 1/2, so that new dimension is 4. And then 1 times 24, that new dimension is 24. And then 12 times 1/3, that's going to be 4. So 4 by 24 by 4, those are the new dimensions. So again, our new dimensions were 4 times 24 by 4. So the volume would be what I get when I multiply those guys together. 4 times 24 times 4 is going to be 384. So the volume is 4 times 24 times 4, and that gives you 384. If I just started with the original volume, remember the original volume was 96. And if I just multiplied the scale factors were 1/2 times 1/3 times 24. My new scale factor is ends up being 4 if I multiply those together. Well, 96 times 4 ends up being 384. So you don't necessarily have to find each individual dimensions. You can find the volume scale factor and multiply that by the original volume. Alright, we're going to finish up with this last problem. I'm going to set it up, we're going to calculate the volumes, and then you will do the cost analysis in the end. So we're all manufacturing engineers today. A manufacturing company needs boxes to ship their newest widget, which measures 2 by 4 by 5 cubic inches. And then standard size boxes are 5-inch cubes. That means they are 5 by 5 by 5 inches big. And they're inexpensive but require foam packaging so we don't damage this thing that we're making. Foam packaging costs 3 cents per cubic inch. And then we could do that, or we can make special boxes that don't require foam packaging, and that is what we're going to compare. So the standard box is 80 cents, and then you got to add this foam packaging. The special box are $3 a piece. So we want to figure out which one's the best deal for shipping these widget things. Alright, so we're going to start with the volume, and then you're going to figure out the cost later. The volume of a widget is 2 times 4 times 5. So each one of those things takes up 40 cubic inches of space. And we're going to assume that it fits in this box, and you can make your foam anything you want. So the box, the standard box, is 5 by 5 by 5. So he's kind of big. He's 125 cubic inches. Okay, that means we're going to need a lot of foam. So the foam ends up being 125 minus 40, and that's 85 cubic inches of foam. So you're going to take that information and figure out the cost of each thing and decide which box is the better deal.